So it's always a tough act to follow Praveen, especially that beautiful talk he gave. And I think when Aditya was scheduling this workshop, I must have drawn the short straw because I'm right between Praveen and Kumar. So can't get much tougher than that. But in all seriousness, it's an honor to be here to celebrate Demos' 65th. I have fond memories of this place, and Demos was the main reason for those fond memories. I think I had a beautiful time here in graduate school. So I'm actually going to switch gears here and take a different tack compared to most of the talks in this workshop. This is more of an industry perspective. And what I'll try and do is sort of set the broader context for the challenges and opportunities that we face in the mobile networks industry. And so I'll talk about what's driving the evolution of mobile networks going from present day 4G towards 5G, and in particular focus on the algorithmic and architectural concepts that you'll see are quite intertwined. And this is joint work with a couple of my colleagues and actually several others. So this is how I'm going to proceed. We'll talk about the drivers of this evolution, primarily the traffic growth that we are seeing, and then the fundamental part pieces to solve this problem. One is around spectrum, another is around sites, and the third is sort of related to both, but essentially looking at spectral efficiency, how to get more bits per hertz per sectors. And then finally, I'll talk about Cloud RAN, which is a disruptive architectural concept that sort of throws everything up in the air with regards to where the functionality is placed and how it interacts. So just to lay the background here, if you look at how traffic has been growing, it's actually been exploding significantly since the advent of smartphones. And in particular, that provides an open ecosystem of apps. And going forward, more of them through social media, video, and augmented and virtual reality. And then beyond that, the sort of hot topic, the new source of traffic would be Internet of Things, not just people, but things connected to each other, and some particular use cases, connected cars, smart cities, smart homes, various verticals like health, industry. So if you look at the traffic and where it stands today, and this is sort of the global amount of traffic on mobile networks, it's about 3.7 exabytes per month in 2015, right? So if you divide that by the total global population, that's about 500 megabytes per month per person, right? And it's about roughly 50% unique subscribers, although the total number of connections is about that much, 7.4 billion. So it's about 1 gigabyte per month per subscriber, right? And then this is growing at about 50% annually, right? So there is still significant growth left in this. And really where this growth is going to come from, or at least that's what's projected, are these sources. So that is really the underlying driver of why we need to evolve the mobile networks. And if you look at the requirements that are posed on the networks, the traditional one is just throughput and capacity, right? And as we move forward, there are more sources of such traffic that would require even more throughput and even more capacity from the networks. But there are other use cases that are developing. So I talked about the Internet of Things. So this may scale up massively, and you may get 10x or even more number of connections relative to the number of connections you have with people. And then yet another sort of prong of this is what's called critical machine type communication, where you require really tight latencies. Venkat and I were talking about this yesterday. So less than a millisecond of air interface latency, and then extremely high reliability, right? So for industrial control and those sorts of applications. Not sure how practical this is, but this is what's projected out as we look towards 5G over, let's say, the next 5 years on what will drive the requirements for the mobile networks. So kind of a big picture view of all the different part pieces that need to be addressed to solve this problem, right? I'm just laying that out here, and then I'll focus in this talk on these couple of pieces. But we're looking at massively scaling the throughput and capacity, massively improving resilience or coverage and latency, but also enabling it for these Internet of Things type of end user services. And that requires a different paradigm for defining the air interface as well as the rest of the network, because these are typically short bursts of traffic, right? So how do you scale at that end of things? And then from a network capability perspective, and especially to kind of make it cost effective, you need a variety of solutions. One of the major trends we see is that if you look at where compute is located in a mobile network today, a large chunk of it is at the base station, and then there are others which are deeper down in the network where you have the core part of the network. But there are other places that might emerge as places to house compute, right, and networking functionality. And one of them is, for instance, the central offices, right? So if you look at wireline networks today, they have central offices, going back to the Bell days, and there are other locations. There are central offices and other switching offices, and then you've got the regional and national data centers. Regional and national data centers do have compute today, but central offices may likely emerge as another place where you house compute, right? So we'll see how that plays a role along with the need to scale up the air interface side of things. And then some of the other things are how do we leverage some of the capabilities and the cost efficiencies driven by software-defined networking on purely the interconnect and transport pieces. How do we make the core part, which is to the first order about anchoring mobility and other subscriber management sorts of functions, to address these new needs and scale it up massively cost effectively. And then beyond that, to open up interfaces on the network which the operator can use to add more capabilities, to automate, to mine the data, use analytics, and so on, right? And so this is how we are tackling the challenges that I mentioned, primarily driven towards 5G. 5G would be a clean slate definition of the air interface, not necessarily backward compatible. But in the meanwhile, the current 4G technology is also evolving and absorbing some of these changes that were sort of originally targeted towards 5G. So then going to this first block of how do we scale the capacity, right? And really no big surprises here, just breaks down into how much spectrum are we throwing at it, how many sites do we have, and how many bits per hertz per sector are we getting, right? And in each of these cases, there are algorithms that come into play to sort of get the most as we look at new challenges in evolving the network. And then as I was mentioning, one of the themes that's emerging going forward is where is this functionality placed? Is it traditionally today it's at the cell sites, but we may have an opportunity to move it to a more centralized location relative to the cell sites, as in those central offices. And then what else can we do with that? So I'll walk through these one by one. So looking at this spectrum situation and what it looks like going forward and what the challenges are, this is sort of the rough situation. Today, if you again take a broad look at the global spectrum situation, and there are many national and transnational regulatory bodies that get involved in sort of making spectrum available to the mobile networks. There is up to about 750 megahertz of spectrum that is available, already allocated and licensed to mobile network operators. The situation does vary from country to country, depending on the local regulators and so on and so forth. But in the good markets where they've got, nice smooth auctioning systems and make it readily available, it's at the high end of that range. And then the bands that are typically available are in the range of 700 megahertz to about 3.5 gigahertz for the mobile network type deployments. Going forward, we have line of sight to more spectrum that will be made available, probably roughly double this, right? And this spectrum will be actually even below 6 gigahertz, there'll be spectrum that might double this in the 450 to 700 megahertz range. 1.3 to 1.5, 2.7, et cetera, and then in the 3 to 6 gigahertz range. Typically, the lower bands have better propagation characteristics and can be used more fruitfully for wide area networking. The higher the frequency, they have typically shorter ranges. But then one of the huge drivers for 5G has been the attention on this centimeter wave, millimeter wave, which are really the high frequencies, 28, 39, 60, 70 gigahertz and beyond, where there's gobs of spectrum, right? So here we're talking about, in these bands, several gigahertz of spectrum. But it comes with significant propagation challenges. So, going forward, when you get more spectrum, there are certain challenges that come up, and we'll talk a bit about that. So one of the opportunities is actually unlicensed and shared license. And typically unlicensed has been used by Wi-Fi, for instance, but it has drawn the attention of mobile operators who see this as also some sort of real estate that they can grab. There are, of course, rules and regulations with regards to coexistence that they must follow, but it is something that the mobile network operators want to incorporate. And so there are issues here in terms of how do you marry sort of an unruly, unlicensed, random access sort of technology with a very tightly controlled, scheduled mobile network technology. And so there are some interesting problems there that we are working on. I won't talk about it today. I already mentioned about these bands that we are looking at going forward. But then one of the challenges that comes, or opportunities that comes with having these multiple bands that you can deploy is how do you actually bond it together? Is there an opportunity to take fragmented spectrum that you may get, 5 megahertz here, 20 megahertz there, et cetera, and bond it together and make it look like one big fat pipe, right? So you can get higher peak throughputs that way, and some of the other benefits are that you can load balance more natively when you bond it like that. So I'm going to dwell a little bit on this particular problem. And that is one of the cornerstones of, as we evolve the networks and we get these disparate bits of spectrum, including unlicensed, how to bond it all together and make it look more seamless. So the problem I'm going to dwell on a bit is the carrier aggregation problem, which is exactly what I said. How do you take two different frequencies? They could be contiguous or they could be quite disparate. And how do you bond it together? And some of the deployment scenarios around that might be where you've got the same set of antennas, these might even be adjacent, and you have the same coverage. So these are the, let's say, 3 sectors from a site, and the coverage areas are pretty much identical. Another one is their orientations are similar, but one's coverage is much smaller than the other, could be a higher band, or it could be because we've used different down tilts on different antennas. Yet another one is where we actually stagger the antenna patterns on the 2 frequencies. So you deploy a different set of antennas and you rotate them so that what might have been, for coverage, essentially, what might have been a cell edge for one frequency becomes center for another. And then a fourth scenario is one where you have what are called low power radio heads that are remote from the cell site, and they have a different frequency and a much smaller coverage. So all of these are opportunities to bond these carriers together, both at the base station side as well as at the UE side. But they get forked and combined over the air. So this turns out to be, when we look at the problem formulation here, it turns out to be common to several different scenarios. One is exactly what I mentioned. You have a few different carriers, and you can think of further granularity within those carriers, but let's say you've got 3 carriers here. You've got a bunch of users, and I can look at jointly scheduling all of these users on all of these carriers, right? So that's a sort of problem formulation looking at joint optimality, where I have one single scheduler scheduling across all of these. Another formulation or another scenario which fits this formulation is one where you've got 3 different sites, and actually it's the same frequency, and hypothetically I consider a user to be schedulable on any one of these, although I may put restrictions, and then I look at joint scheduling a user across these 3 cells, right? But in practice, I want it really to be scheduled on just one. And then yet another scenario is, let's say in the 5G context, where I have maybe even a contiguous amount of spectrum, but it's a large chunk of spectrum. There is a scalability issue with actually jointly scheduling all the users on a large portion of the spectrum. This complexity actually grows superlinearly, both in the number of users and in the number of what are called resource blocks, or these further granularity pieces. And so it would be helpful if I can divide and conquer this without much performance penalty. So that's the problem we want to look at. So one way of modeling and solving this problem is, if you take a user, and on each one of these cells, so cell is now a cluster of resources, however I've partitioned my resources, and I look at scheduling a user on different cells. And so let's say it gets a certain spectral efficiency or a certain rate on each one of these cells. And from each cell C, the user U gets a fraction of the resources in that cell, let's say rho sub CU, right? So the total amount of throughput the user would get is this quantity when you sum the fraction it got times the rate summed over all cells, right? And the objective here is to maximize some utility function that the user gets as a function of its throughput. So a typical choice of utility function is the log, but there are other forms that we could do, right? So that's the problem we want to solve. And for this modeling and solution, we'll assume that these rates are fixed, although in practice they'll be time varying. So if you look at this problem, right, and you can find a solution to it, and what the solution says is that this resource allocation to the different users in different cells follows this following property, that if you look at the rate of the user divided by its throughput, it will equal a constant if it is getting an allocation that's positive on that cell. And it would be less than equal to this constant if it's getting 0 allocation, where these are essentially some cell-specific constants. So for each cell, you can find a quantity, and it's a threshold rule. If this rate, of course, this throughput in turn actually depends on these allocations, so it's a little circular over here, and we need to solve this. But if that rate over the throughput is equal to this quantity, which is actually captures the load in the cell, then you would get a positive, sorry, if it gets positive allocation, then this will be equal, and it'll be less than that if it got a 0 allocation. So basically, what you need to do to figure out which cells a user would be assigned to is to look at the rate divided by this constant, and I still need to find out what this constant is, and find the cells which maximize this. And those are the cells that the user would be allocated to. And the interpretation of this cell-specific constant is as follows. If beta is the fraction of user's U throughput that it got from a particular cell, so for user U, for cell C, if you look at the amount of throughput it got from cell C divided by the total throughput, and for the cell C, this particular constant is just the sum of these quantities, right? So in particular, if these betas are just 0 or 1, meaning the user is scheduled exactly on one cell, right, then this particular quantity is just the number of users scheduled on that cell, right? So that's the load, right? But it addresses many other cases. So in practice, the way you find these allocations and the way you find the loads is actually to run a scheduler per time slot following a gradient method, right? So you take the utility function, you take the gradient of the utility, and schedule the user that maximizes the gradient. So that's what you're trying to maximize. And we had a result going back with Vijay and also Sasha Stoliar quite some time back, which basically proves the convergence of this gradient method to an ODE, and the equilibrium point of that ODE turns out to be the optimal solution, right? Okay, so now, all of this put together gives us a way to construct an algorithm, right? Each cell scheduler calculates these cell-specific loads. Actually, the cell-specific load is nothing but this proportional fair metric, which I was showing on the previous slide, this particular quantity. And so each scheduler calculates it in the step one, exchanges it with all of its neighbors, and then at each of these, if that particular cell is responsible for a particular user, it looks at these quantities and decides which cell a user should be associated with. And it basically picks a neighbor cell or picks one of the cells which maximizes this and assigns the cell to it. Okay? So you end up with a structure to this algorithm where you're running a scheduler, you extract some metrics from the scheduler, you exchange it with your neighbors, you make decisions on this, which user is associated with which cell in this particular case, inform all the neighbors, and then each of those neighbors are running their own scheduler. So it's a way of constructing a decentralized algorithm with some parsimonious exchange of information amongst these schedulers. So if you look at the kind of simplification you get, you started with a joint scheduler where all the users could be scheduled on all of the resources. We partitioned this so that we are running per cell schedulers. However, users may be scheduled on all of them, on multiple of them. But it turns out in practice, and in theory as well, that very few users actually straddle the cells, right? So between two cells, actually, you can prove that there is at most one user that will straddle. So with this further simplification, you've got almost a partitioning of users into cells, right? And that sort of makes it at least linear at that granularity. Okay, so let me switch now to the other pillar, moving on to cell density. So again, kind of looking at global statistics, if you look at the total number of macro sites that are there globally, it's at about 3.7 million cell sites globally, right? And again, doing the math with the number of subscribers, it's about 2,000 subscribers per site is what we have, right? And again, density varies. In dense urban areas, you may get more. But typically, we're trying to scale the number of sites, and on top of that, the number of carriers with the subscriber base. And this number is growing by about 8 to 10% a year. And then the other part of it is, besides macro sites, we have small cells. And the characteristic here is traditional macro sites are such that they butt up against each other and they're dividing the coverage, right? So it's a catchment area that's dedicated to a macro. But when you deploy small cells, they might be entirely within the coverage of a macro and are added there just to add capacity, right? So small cells promise an even faster growth. Of course, they are still at an early stage, right? And these sites are now going to be added largely for adding capacity. They're not so much for coverage. Coverage has largely been addressed. And what happens when you do that is interference becomes a significant problem. So you need algorithms to address interference issues. So as I was mentioning, if you look at this sort of small cell or HetNet deployment, you may have the coverage of a macro area that's fairly large, and then a small cell which occupies a small portion of that entirely within the macro area's coverage. And in this case, you actually have a strong signal both from the macro and the small cell, and one of them is interference, right? Unless we're doing some kind of joint reception or joint transmission comp. So one of the problems to look at here is what's called inter-cell interference coordination. And the technique here is essentially, let's say for the macro-based side, to mute for some time some resources so that what was interference goes away, and you get a better signal to interference SINR at the handset, which may be attached to the small cell, right? So now the question here is, how much muting should the macro cell do for the benefit of the small cell guy, right? Because clearly it's trading off capacity on the macro cell for benefiting the small cell, right? So once again, we can look at the same problem where we look at individual users' throughput and a utility of that and maximize it with this parameter, which is the amount of the fraction of muting I do on the macro for this purpose. And the associated problem of scheduling is still there, which is what fraction of the resources in a cell are given to each user. And it turns out that, without getting into too much detail here, the way we sort of solve this problem is it's similar to what we did before. You partition users into users that are associated with a macro, and within the PICO, you consider two sets of resources. Resources that are there when the macro is muted, and resources which are there when the macro is not muted. Think of them as two different cells. Call them the ABS cell and the non-ABS cell, and then we are looking at resource allocating amongst these different cells, while at the same time scheduling in these cells. And it turns out that this resource allocation problem can be solved, and the fraction of muting is simply given by the number of users in the muted cell versus as a fraction of the total number of users, right? So it has a nice simple interpretation. And then we can tie back this quantity, actually the number of users. This is actually a simplification. In more generality, it is tied to this quantity, the cell-specific load that I was talking about before. And all of this, these formulae I've given are in the context of a log utility function. It can be generalized to other utility functions as well. Now let me move on to some additional problems that show up when we look at spectral efficiency techniques, again, still primarily arising due to issues raised by adding much more spectrum or densification, in particular interference sorts of issues. So again, many techniques. One of them is around power control and muting to reduce interference. Other interference management techniques. Massive Mimo is a whole different dimension which could be lumped into this spectral efficiency area. And there are other techniques such as dynamic uplink and downlink resource allocation, so divvying up time between downlink and uplink. Non-orthogonal multiple access, so scheduling multiple users on non-orthogonal resources. Separate association of users on uplink and downlink on the control plane versus user plane to address, again, different coverage and capacity sorts of situations. And again, these can all be cast back into those kinds of optimization problems that I talked about. And then going towards more of a clean slate with 5G, the whole frame structure is being changed, right? So currently the time slots, or what are called TTIs, are 1 millisecond long. We're looking at perhaps 200 microseconds or 250 microseconds, and also flexible durations of these TTIs. So there are a number of things that are being played around there to address those problems that I mentioned at the beginning, in particular, things which may have very tight latency requirements versus things that may have not so tight latency requirements but are keen on getting high throughput, et cetera. So I'll dwell a bit on the first two and skip the others here. So for that first problem, sort of the simplified toy version of the problem is a particular cell, you may want to mute it or lower its power when you look at this particular scenario, right? So when you mute this particular cell pays a penalty because it can no longer serve its users, or even if you reduce its power, the spectral efficiency of the users in that cell goes down. But when you do that, there's less interference to the neighbor cells do benefit. You can look at the net utility benefit as a result and decide that you want to take this action if that net benefit is positive, right? And that's a local myopic decision, but you may want to try that out. So just keeping that in mind, some of the key questions that actually we need to address when designing these schemes is which cells should coordinate. So when this cell is looking at muting, who else should it look at to determine if they benefit from it or not? Should these algorithms be designed in a centralized or decentralized fashion? What information should be exchanged? How often should this be exchanged? And how often should this, how many iterations do you need to do? Do you have to do many iterations within a time slot to get some kind of decent convergence? Or can I do it just one shot in each time slot and rely on some kind of continuity across time slots? Because not everything is changing from one time slot to another, right? And then lastly, and this comes up in this architectural context, because this coordination may have some bandwidth and latency restrictions. So how do I factor that in? So, I mean, one of the things around interference is it's a local problem, right? I only get interfered by my nearby neighbors. So even if the totality of cells is large, really you just need to look at close by neighbors in order to address this problem, right? So you can look at cell-specific clusters. You can look at, when I'm deciding whether to do something with regards to muting or lowering the power of a particular cell, I can look for some limited set of neighbors. But can we come to this decision making, in a distributed fashion? Because there are ripple effects, right? If I decide to mute for the benefit of others, it has knock-on effects, because what then gets done in the next cell determines things further away, right? And then how do I make these updates? If I share this information, does every cell update its power level, or only a smaller subset does it? Because they may be working at cross purposes. So this notion of independent sets, by the way, is one where if I have two cells such that their per cell cluster, which is the cells they factor into making this decision, are disjoint, right? So when you update simultaneously on these independent sets, there is no such conflict that you're doing things at cross purposes. I think I articulated many of these problems before, but basically we want to identify insights from theory that allow us to design decentralized mechanisms, because centralized mechanisms really don't scale very well. So in particular, we have a result here, but I think there's a lot more to be done in this space. If we take that spectral efficiency to be, let's say, log of 1 plus SINR, and if we take the limit point of any power sequence that is generated by this sort of decentralized coordination mechanism, where we are either updating exactly one cell at a time, or we are updating on this using independent sets. So for instance, if you took this kind of hexagonal layout and the per cell cluster was just the immediate 6 neighbors, you could use 7 colors to color the whole, tile the whole cell layout. And then you could update on 1/7 of the cells simultaneously, right? And in 7 iterations, you would cover all the cells, right? So it's not as bad as the sequential case. For this particular problem, it's a non-convex problem, right? Because you've got power showing up both in the numerator and denominator over here. However, if we linearize around the current power levels, and we use this kind of an interference price to signal to the neighbor what the relative, what the marginal improvement would be if it lowered or increased the power level, what we find is that the value function improves at each step. The limit function satisfies the KKT conditions, but we're not necessarily getting convergence to an optimal point, right? Another variant on this is, instead of looking at this linearized version, if I actually have my local utility function and the utility function of my neighbors, and I optimize that at each step using the same restriction, then too I get I get these properties. But in addition, I have the property that on any one cell's power, I also have optimalities. That is, just by changing one cell's power, I can't do any better. Some simulation results around that. I mean, maybe I'll skip that. The point I wanted to make with this slide is here, we didn't talk about what are the interconnect latencies amongst these cells. In practice, these might be distinct sites which have some interconnect latencies, and there is an impact on the performance of these coordination algorithms due to latency. And if you look at the ideal case, and again, I'm not showing you the performance numbers here, you get a certain amount of improvement. And what we found is, for a suite of such algorithms, I talked about the ICIC algorithm, I talked about carrier aggregation, coordinated scheduling is what I just talked about. We talked about point selection comp. You can still harvest some benefits. If you go to one-way latencies, which are of the order of 5 milliseconds, where the time slot is a millisecond. And some of this is tied to the nitty-gritties of the protocol, air interface protocol, and the timing loops within that. But others are part of how fast the channel is varying and so on and so forth. Maybe I'll just do a quick intro on the massive MIMO topic. So again, this takes different forms and different form factors when you're looking at different bands. So if you're looking at the low bands below 6 gigahertz, at, I think, if I remember the math right, at 600 megahertz, if I'm looking at 4 antenna elements spaced apart half lambda, I'm looking at about a meter height, right? So whereas if I go to 60 gigahertz, that's 100 times, right? It's much, much smaller. And we can look at chip scale antenna arrays in that case. But in both cases, one is looking at 2D antenna arrays, right, to essentially not just do beamforming in the azimuth domain, but also in the elevation domain. So if you look at sort of the problems, and I'll just talk a bit about the problem formulation here and not the solutions. There are problems on the phi and RF side, which are looking at, what is the set of beams that we work with, right? The beam space design. Is there any structure to that beam space? In particular, do we form beams first on a common or a cell-specific fashion rather than a UE-specific fashion, or do I do a combination of the two? Is the beam forming in the baseband domain, or is it in the analog RF domain? In RF domain, it would be basically phase shifts. Or is it a hybrid? Is the beam space discrete, or is it continuous? So in the discrete case, it could be a hierarchical, multi-level beam space, or it could be some other grid of beams, and you're trying to do beam selection amongst them. Or is it more continuous? And typically that's feasible only with in a TDD system based on uplink pilots, right? So you can actually estimate the channel rather than having to rely on a discrete feedback from the user. Then the other problem here is on pilot design and channel estimation. So how are these common or cell-specific beams chosen? How are the UE-specific beams chosen, right? So what affects this is also, do we have reciprocity with TDD? What kind of uplink pilots do I have? What kind of downlink pilots do I have? What kind of feedback mechanism do I have based on the downlink pilots? And we could use a combination of the two, right? So that sort of lays out the problem space on that side. And then kind of looking at the scheduling, resource allocation, radio resource management problem, there is a pilot management problem. How often do I use these pilots, and which pilots do I use, right? Because that's occupying space that could be used for data, and there's a clear trade-off between learning and optimization there, right? You may already know this is a good enough direction, but should I keep betting on that, or should I explore more widely because things may have changed, or I might be missing out on something that I don't know. Beam scheduling, right? How often do I schedule which beam? Or how often do I schedule a set of beams simultaneously, and which set of beams? So this actually turns out to be a resource allocation problem, similar to the problem we were talking about, how much resources to allocate to the muting portion and the non-muting portion. And then how to map users to different beams. And this is similar to the cell selection problem I was talking about. And then there's a power control problem, which is how much power to give on the different beams. And this is similar, again, to the power control or muting problem I was talking about. And in all of these cases, what you'd like is a scalable solution which operates on a fraction of the problem and coordinates amongst those fractions. Okay, so finally, maybe to try and just expose you to this topic, the problem with centralized or Cloud RAN is the following. If you look at today's deployment and you look at cell sites, you have the majority of the air interface functionality at the cell site in what's called the baseband unit, right? So there is an RF portion which is fiber connected to this baseband portion. Typically that's DSP that's doing that processing, and then backhauled over an interconnect network to the core and sent out to the internet, right? Large sites with some remote radio heads may actually pull together and aggregate a number of different such RF nodes. Now, what is being considered going forward is to pull back some of these compute nodes from the cell sites into locations like the central offices that I was talking about. And here, to begin with, you could just do a rack and stack. Basically take the same units you had there, just pull them back, stack them up. What does happen as a result is that the interconnect between them becomes local. So you have fast interconnect between them, but you have to worry about the latencies and bandwidths on these links. But then the next thing you could do is not just leave it as these discrete compute units, but rather take a pooled compute unit, right? And in fact, move the functionality to generalized to GPPs, right? And use many other techniques which are around cloud and computing and so on and so forth to kind of get more efficiencies out of this. So that's sort of the next frontier that we are looking at. So there are a number of challenges in especially this last step. We would want to move that front haul connection to more of a packetized Ethernet connection to combat the requirements on latency and bandwidth. Move things to these kind of server platforms for cost benefits. You need to re-architect the software and things, sort of akin to how we were scaling things. You want to break things down into functions that are really tied to the user and functions that are tied to the cell, and then kind of construct those cells appropriately. Multi-cell coordination, as we talked about as well. So I think maybe a big picture view on this functional architecture piece is, as we look at where things are today and as we are moving forward, you have some ends of it which are nailed in the ground, right? So you have cell sites, that's one end of the network. You've got the point at which you egress the traffic into the internet, that's another point. And then you have these locations like central offices and so on where you could locate compute. You've got fiber runs. But the question is, if you take the baseband, the functionality, the PHY functionality, the scheduling, MAC, et cetera, where do you locate them? And there is an option now, sort of a clean slate, move it around to a location where it makes sense. And what we've got to worry about is what impact do latencies on this, so to say, front haul have? What effect do latencies on this side haul or back haul have as we look at these functional architectures and the algorithms? So both protocols and algorithms get impacted as a result. So I'll just wrap it up. Traffic growth and these new end user services such as IoT are really driving mobile network evolution. Spectrum addition across these different bands, including licensed and unlicensed and likely licensed, is happening, and they offer up various opportunities and challenges. Getting a fair bit of site densification, primarily with small cells and het nets. Algorithms to combat these new challenges to spectrum addition, site densification, et cetera, are certainly needed. And they all require some form of multi-cell coordination. And decentralized algorithms is really the way to kind of do this scalably. And massive MIMO is yet another important dimension to skinning this cat. Several other spectral efficiency techniques as well. There's a disruption looming on the architecture side, which sort of gives us a clean slate to place functionality, albeit subject to certain restrictions. And just to summarize, both architecture and algorithms, as you can see, are quite intertwined and are key to driving this forward in a sort of systematic fashion. So I'll stop here. I don't know if you've got time for questions.
These are the uncertainties at each time, and a vertex is like a state. Okay. Now we know that stationary policies are optimal. Tree policies are optimal. Tree policies are actually a little bit fine.